let's go over a quick intro to the design calculator that we're going to use for this season. The design calculator essentially is a spreadsheet that tells you or helps you calculate what are the distances needed for your power transmission runs from your motors to your different systems. So like belts, just like this. How far does this belt have to be from this, or this pulley need to be from this pulley, or this pulley need to be from this pulley in order to have an appropriately tensioned belt. These belts and pulleys kind of operate together and need the same pitch. So the pitch for the belts and the pulleys and the gears are the distances that the teeth are spread apart. So like you could measure it from the top of this tooth to the top of this tooth, or the bottom of this to the bottom of this. The pitch is just that distance, right? So when we say 30 teeth, that means there are 30 of these teeth in this belt or on a pulley, and they're spread apart. When we say a 5 millimeter belt, that means they're 5 millimeters apart. With the gear, so this is 20 dp gear, is one of the most common gear sizes for FRC. 20 dp is diametral pitch. That means that these teeth are spaced out so that there are 20 of these teeth per every inch of the diameter of your gear. So that's what those values mean. So this is what the design calculator looks like. There's a belt section for belts and pulleys, a gear section for meshing gears or spur gears, and then a chain and sprocket calculator. And the chain and sprocket calculator and the belt calculator are essentially like they're very similar. They're the way that they work. So we're really just going to talk about the belt and the gear for today. And so all the belts that we have in shop are 5 millimeter pitch. It's a relatively common size. There's also 3 millimeter for FRC, but everything that we've got in the UNLV shop is 5 millimeter. Typically, the things that is locked in is the belt size. So belts are products that you would buy, and you wouldn't really be able to modify the size of the belt unless you buy a new belt. So usually there's an inventory of that, and we lock in the belt size and then figure out what pulley sizes work with that belt, because pulleys can be 3D printed. Same thing with gears. Gears can also be 3D printed. So like for example, if I have a robot here starting a main sketch, we have the drive base, we have the bumpers here in orange, the size box, and then this intake that was sketched that's going to just like fall down and then come back up to pick up game pieces and kind of bring them into the robot. Let's say we want to drive this top wheel here. So I'm going to start a new sketch, and I'm going to call it motor, or let's intake pulley run. Okay, so on that sketch, I know I'm going to have a motor somewhere. That motor is going to have a shaft. So I'm just going to draw a circle to represent that. And then I'm going to draw a straight line going from that circle to this wheel. All right, and let's say that looking at the belts that we have in shop, we know that we have, we'll do a 100 tooth belt, right? We know we have a 100 tooth belt. Looking at this, just generally, the motor probably should live close to the pivot is best, but let's say we want the motor to live somewhere right over here, right? So we got 7.69 inches. So what we'd want to do is we could figure out what set of values kind of get us close to that. So I usually start with 18 and see what that looks like, because 18 is kind of like the smallest pulleys that we could print that have a decent amount of strength for a 1/2 inch hex shaft. Anything smaller than that, the amount of filament between the shaft and then like the teeth get kind of small. And so that's kind of where we start, and we're seeing it's about 8 inches, a little bit more than 8 inches. So we could actually toy with that a little bit. If we wanted to get closer to like 7.5, we can do something like 20 to 20, and we're at 788. Maybe we want to gear it up a little bit, have a little more torque. We can have a differential in these values. So do 18 and 25. And now we're looking at like the kind of close to our value. Okay, let's say that works here. 18 to 30, we have a 1.67 gear ratio, so we're getting a little bit of torque out from that. And the center to center distance is 7.47. So here I would have this 7.47. and that would be that distance. And so let's say we're using a motor, and we know, I think for like a Neo, the diameter of a motor is around like 2.5 to 3 inches. So let's say we know that the motor diameter is something like 2.5 inches. And when the motor flops around, we don't want it to hit like the bumper structure. So we give it a bit of a distance from the bumper structure. So let's say we want it to be at least 1.5 inches away from the bumper, so that way we know as the intake falls over, it's not going to hit any of the structure down here. So that kind of locks us in that dimension. You see that these turn black. I don't need that line anymore because I have the motor diameter. So from the center of the motor to the first wheel, using 18 and 30 tooth pulleys, a 100 tooth belt, we have our first pulley run. And let's say we wanted to add a meshing gear to reverse this wheel down here. So what we'll likely do is we'll likely have a couple of meshing gears, one meshing gear probably on the shaft below, another meshing gear right above it, and then we'll need some sort of pulley and belt to go from the top wheel to the kind of middle shaft, right? And so we would do a very similar process. So we're looking at about 5 inches here. And so let's say I have a couple of gears that I want to use, 20 dp. Let's say we don't want to have any gear reduction, so we'll have something that's kind of 1-to-1. And so there's no gear ratio here to increase torque between the top and the bottom wheels. For the gear meshing calculator, we typically have a little bit of an offset as a default because the gear don't mesh perfectly from center to center. There's a little bit of space that you need to give for the teeth to actually kind of engage smoothly. So we add typically a 0.003 inch bump to that dimension. And so my center to center gear value is 1.503. And we see that the diameter of those gears is 1.5. So I could actually dimension these as 1.5 to kind of show what the size of the gears would look like. And then this was the 1.503. So you could see like these gears would kind of touch each other. Next we want to see, okay, 5.25 about. So again, I don't want to have a gear ratio, so I want these two numbers to be the same. Let's say I have another belt that I think 70 is one of the other belts that we have a lot of. So if I start from 18 to 18 for the 70 tooth belt, I get about 5.12. Let's see if that fits. 5.12. Cool, and that seems to fit. And so essentially I can now design an intake, and I know I'll have a hole here for the first wheel, a hole here for the reversal, or a hole here for the bottom wheel, and then a hole here to mount the motor. So that's kind of how we design powertrains using the design calculator for belts, pulleys, as well as gears. Now here's an example intake with kind of the same idea here. It's a flip down intake that has a motor mounted right over here. That motor runs to the first set of top wheel here, and then it goes across. That shaft is still spinning, rotates this pulley out here, goes down and turns this meshing gear, and then this meshing gear runs a slower gear that spins the bottom shaft. And then you could see for that intermediate gear, you do want to have two sides or two bearings to kind of help that gear rotate. If this wasn't here, this would kind of be cantilevered around the center. It would technically work, but it would be rather weak. This thing would bobble around a bit. It wouldn't be fully supported, and that would make the meshing of the gear here kind of not consistent, as well as the tension of this pulley would be inconsistent. So you really want to have your shafts constrained at a couple of points to make sure that that shaft is rotating true as it's spinning.